Good afternoon, everyone, and welcome to today's sponsored ABC webinar, Shared Success, Customer Collaborations in Biogas, RNG, and Carbon Capture. My name is Caroline Pete, and I will be facilitating this webinar. Before we begin, I want to thank Vysela for sponsoring today's webinar. Their sponsorship directly supports the ABC and our programs. Thank you, guys. Before we start with our presentation today, I want to go over just a little bit of housekeeping. You should be able to see my slides titled Quick Notes, and you should be able to hear my voice. If you're hearing echoes or your sound quality is bad, you can change your settings in that audio pod and the GoToWebinar toolbar, which should be on the right side of your screen. You will get the recording and the slides after the event, probably by Friday. Just give me a few days. We'll send you all of that. So if you miss anything, you'll be able to review. You can also ask questions at any time during this presentation. We will be handling the Q&A at the end of the presentation, but you can ask questions at any time using that questions pod, which is in that GoToWebinar toolbar on the right side of your screen. If you're still having any trouble, send the organizers a message using that questions pod. We'll be able to help you. You can also send us an email and we'll be able to help you there. So with that, I'm going to hand things off to our moderator today, moderator and speaker, Justin Walsh with Vysela. Justin, please take it away.
Thank you very much, Carolyn. Joining me today here is Antti Heikkilä. He's a product manager for some of the biogas, RNG, and carbon capture products we have here at Vysela. And we're joining you today from the Vysela headquarters just outside of Helsinki, Finland. Current time is about 8 p.m. And so we are hanging in there today, coming to you. So thank you all for joining us. Next couple of slides, please, Caroline. I think there was a housekeeping slide we needed to skip over on this one. And we're not seeing it. There we go. Nope. Going to go back a little bit if you would. Yeah, there we go. Thank you. And so today we're going to be covering some of the customer cases and some of their applications that we've been working through over the past few years in a few of these key applications that we've been working with recently. The first is cogeneration, so a combined heat and power generation at an anaerobic digestion plant. Then we'll also talk about a biogas upgrading to RNG operation. And then we'll round out with some carbon capture applications that we've been involved in. This is an emerging market for us and becoming more and more relevant for the biogas and RNG community. So I thought we might share some good stories that we've developed recently here on the topic. So next, please. But before we get into that, I'd like to introduce Vysela for some of you who are a little less familiar with us. We began in weather measurement over 85 years ago, and about 50 years ago, we developed the first polymer humidity sensor. Since then, we've been adapting these sensor technologies to a variety of industrial applications, from life science, museum art preservation, HVAC, and we've even been the technology chosen by NASA to help find water on Mars with our low dew point technology. We consistently invest over 10% of all of our revenue in R&D each year to continue to develop products to serve these wide variety of industries, to help protect products, improve processes, and protect personal safety. So next, please. And then just a little bit more about ourselves. So I'm an application engineer working in business development for, like I said, the biogas, RNG, and carbon capture applications for Vysela. Later this month will be my 10-year anniversary with the company, so I'm very proud to be here. My background includes an engineering degree and over 20 years of electrochemical measurement technology experience from a variety of different companies, from other sensor manufacturers to the private sector, working with the EPA. And then I'll let my colleague Antti here introduce himself as well.
Good morning. My name is Antti Heikkilä. I am the product manager at Vaisala for our multi-gas probes product line. That is those infrared probes that we use for monitoring other gases than carbon dioxide. Carbon dioxide is currently the backbone alongside with humidity of Vaisala's product range, but all the other instruments, methane included, are in my portfolio. My background is in infrared spectroscopy. I used to work with another company doing mostly emissions monitoring with FTIR technology, and as part of that I have been contributing to different international standards and ASTM test method revision for FTIR spectroscopy and NDIR such as CO2 standard reference method documents.
Very good. Thank you, Antti, and yeah, thanks for hosting again. Next slide, please. So these case studies are going to be based around our MGP 260 series products, the ones that Antti here is responsible for. Like you said, they measure methane, water vapor, and carbon dioxide, primarily designed for the biogas and renewable natural gas applications. We've also found considerable success adapting these into carbon capture applications, which we'll talk about a little bit more. These are self-contained units with no moving parts, requiring no sampling systems, no consumables, and very low maintenance. Next slide, please. The series consists of two models, the MGP 261 and the MGP 262. The 261 being the full-featured, full range for all three parameters that we offer with this probe, with high accuracy and the ranges that are typical for anaerobic digesters and some landfill gas operations. The MGP 262 is a high accuracy, low level methane analyzer combined with a full range CO2 sensor with high accuracy at the higher range for the CO2 measurement. Again, very highly accurate and self-contained. They are rated Class 1 Div 2 for the United States and ATEX Zone 0 for the European and other markets. They contain three 4 to 20 milliamp loop-powered outputs and Modbus RTU communications, as well as an isolated EX-rated input for a pressure sensor or a temperature sensor, should you choose. Next slide, please. The way they work is with our patented CarboCap technology. This is a version of an NDIR sensor that we develop and manufacture here in our own clean rooms. Clean room I actually took a tour of this morning. So very impressive operation here. What sets these sensors apart from traditional NDIR sensors are two main factors. The first is the light source that we use, which does not dim over time like a traditional NDIR sensor filament bulb would. So the filament bulb dimming is one of the main reasons for drift in an NDIR sensor, and we've all but eliminated the need for frequent calibrations to eliminate the drift from that light source. The second main thing is the detector itself that we've chosen to use, which is a miniaturized form of a scanning spectrometer. It's a very impressive little piece of technology that scans between the measurement absorption wavelengths of the three gases that we're measuring, as well as a non-absorption wavelength. So effectively creating a zero calibration every 8 seconds within the probe. This eliminates the need for attempting to introduce ambient air into the sensor to kind of assume a zero calibration. And the sensor elements themselves are protected by a sapphire glass, which makes these highly resistant to most contaminants, and they have been tested with exposure to high levels of H2S with no degrading effects.
Yes, we did like an accelerated testing with 1 volume %, 10,000 ppm hydrogen sulfide in saturated humidity for 1 year, didn't see any degradation whatsoever. So one can then infer that it would last for at least 10 years in the presence of 1,000 ppm hydrogen sulfide. I'd like to add to what Justin already said in that with the miniaturized interferometer that we have in front of the detector, we can do scanning of the spectrum, so that enables us to measure 3 gases at once with an NDIR, and one of the gases is water vapor. So this is the groundbreaking innovation that enables us to measure in situ in wet gas with an NDIR. Traditional NDIRs need to have humidity removed because it would interfere with the measurement of other gases. And besides having excellent stability in the light source, the fact that the light source is also a miniaturized device that consumes very low power, that gives it a much longer lifespan than other solutions. So we don't have to replace infrared light sources ever in these probes. The light sources are designed to last for the lifetime of the probe, which is more than 10 years.
Yeah, thank you. So yeah, we'll move on to the next slide. So just again, highlighting some of the applications that these probes were designed for: anaerobic digesters, landfill gas upgrading, pre and post treatment. Like Antti said, they're designed to measure in wet gas, so straight off the digester, right out of the landfill. These are very robust instruments that can measure directly inside the process. Combined heat and power engines very much benefit from the fast response time and real-time methane measurement, which we'll talk about in one of these case studies. And RNG upgrading. The 262 is a very good tail gas monitor, which we'll mention as well. And then in carbon capture applications, measuring in situ, good for point source and direct air capture systems in multiple locations, either in the emission stack themselves or in the captured CO2 streams. They're very versatile, easy to use and integrate into some of these systems, both in research lab grade, as well as some of the pilot plants and scaled up versions that we're starting to see. Next, please. So jumping right into the case studies, well, jumping in now anyway, we're going to begin with one of our earlier cases, which comes to us from our friends in Japan at JFE Environment Technology. This is at the Muria Biomass Center, where they are composting a lot of agricultural and food waste and converting that into biogas to fuel a combined heat and power engine. And so Antti was involved in the development of that project. And so one of the first questions would be just, what were some of JFE's primary concerns and how did we address those?
Their main concern was that they had observed seasonal variation in their methane concentration in the biogas. They are using basically daikon radish as their feedstock. So right after harvest, September, they have a sugar-rich, high methane potential feedstock. And then as winter progresses, the quality of the feedstock goes down. And at the same time, when it's colder, this is in an exposed location next to the sea, south of Tokyo, they saw a decrease in their methane concentration, increase in their CO2 concentrations, and they had to adjust engines accordingly. And the problem was that when they didn't have an instrument that would give them continuous readings, they were relying on manual testing. So a technician was taking samples with a portable NDIR like once per week, and they were not satisfied with that sampling frequency.
Yeah, we see that a lot for some smaller systems and systems without a lot of monitoring or the ability to monitor. So how it's been, a couple of years now. How are things running there? What kind of feedback have we gotten?
This one has actually been running now for at least 4 years. It was this was our first installation in Japan, so I was involved in both the kind of the pre-installation planning visit and then during commissioning, and we have had very good success with them. They, well, being Japanese, they want to take best possible care with things like instrumentation, so they continued doing their manual sampling. They also took bag samples to a laboratory, so we were able to compare 3 independent testing methods, one of them being our instrument, and we saw that our instrument was more consistent with the laboratory analysis than the instruments that they were originally using. In fact, when we first commissioned the instrument, their impression was that our scaling must be wrong because the results were much lower than they had expected. But when they took out their own instrument and measured with that, they were convinced that yes, it is actually 40% methane instead of 55, which they were expecting. So for them, it was like a big revelation that the plant is not running nowhere near the efficiency that they were expecting. And with online measurements, they have been now able to increase the efficiency, and especially they have discovered that they need to increase heating and mixing rate in winter time to keep that kind of low methane potential feedstock performing. Since this is next to Tokyo Bay, they have had a couple of earthquakes, at least 2 typhoons and 1 tsunami. As you can see, this is outdoors, and I'm happy to say that our IP65 rating really holds true. It is waterproof.
Actually, these ones are 66.
Yes, it's 66.
Actually, yeah, I forgot to say next slide, please. So, Caroline, if you wouldn't mind. And one of the things that I did want to ask about next, and well, actually, just step back for just one moment. I would just have everybody please ask questions at any time. I see a couple coming in here that I'm going to address just because it's relevant here, but we're going to answer most of the questions towards the end. But these are just relevant for this one here. So first, somebody asked, are these resistant to siloxanes? And the short answer is yes. It's not going to ruin these probes in any way, but siloxane buildup on the filter element itself can cause problems over time. But the solution to that would be just to replace that filter. And then well, it's unlikely that any would get inside the filter, but the sensor element can be cleaned in the field. The filters are readily available and inexpensive, and so you could just check that every once in a while and replace it if needed.
Yeah, we recommend inspecting the probe once per year, but we have landfill gas customers who haven't done that. They have been running for like a 2 or 3 year replacement interval. After all, in an in-situ type of instrument, we are not actively pulling gas through those filters with a sample pump. So even though the filter might be dirty on the outside, dust particles and VOC liquid like siloxanes, they don't really work their way deep into the filter, so the filters last for a surprisingly long time.
Yeah, and you see this in this picture here. It is mounted directly in the pipe. This is about a 4-inch pipe here. There was another question about functional pipe diameters, and we don't have a maximum, but the minimum is pretty much going to be 2 inches with an offset. So that's about as small as we can really get. Now, that said, we do have a flow-through chamber accessory. So you put the probe into there, and then you have a 1/4-inch, say, stainless sampling tubes that you can run an inlet and an outlet. So we can facilitate remote installations as well. But all right, let's move on to the next case, please. Which is biogas upgrading, and this is a name that most of you will probably recognize. Pentair is the manufacturer and supplier of RNG upgrading systems that you can install at these plants. And this case comes from the Netherlands at the Sustainable Fuel Plant in Zeeland. And I'll just ask for the next slide too before I forget. So here, Antti, if you would give us a little overview of their type of system and what they needed in terms of measurement from us.
Pentair offer a membrane system for upgrading biogas into RNG. It's a two-stage membrane setup, and they needed instruments for measuring both the incoming biogas and then tail gas, which is mainly CO2. They can also have instruments for measuring calorific value or BTU meters at the point where they transfer RNG into the national grid, but they wanted to control the process better by having online instruments also in the incoming gas stream and in the off-gas stream.
Yeah, very good. And what were some of the biggest challenges of measuring in their particular system?
One of their issues that they wanted to kind of improve was the drying of biogas before it goes into the membrane systems. And before the MGP product line was launched, there really wasn't an online humidity sensor that would work satisfactorily in biogas. In a membrane upgrading system, you need to increase pressure, in their case to over 10 bar, and as you increase the pressure, you also increase the dew point of the gas. So they wanted to know the dew point of gas before it goes into the compressor, because if you get condensation after a compressor, you don't have a natural easy way out for the condensate, and it's bad for the membranes if they are coated with water. And also, as they are utilizing their off gas as bio CO2, it's sold into greenhouses for elevated CO2 levels in greenhouses to promote plant growth, or they use it as a refrigerant in food and beverage industry. So they needed to also have a handle on the quality of the CO2 gas that they extract from the tail gas.
No, that's very good. And as we're figuring out more things to do with that CO2-rich tail gas, we're going to start, looking at all the different options and use cases and potential markets for them. And one of which we'll talk about a little bit later in this presentation. So moving on, next slide, please. So bridging the gap between, anaerobic digestion and upgrading systems can be, test units. Our distributor in the UK, Bohr Limited, has developed a portable sampling system, essentially, for a probe that doesn't require any sampling systems. But that said, it just expands the range of possible applications for this type of sensor, and opens up the possibility for other operations to kind of test it out, see what benefits measurement and quality online continuous measurement can have for their operations. So yeah, I said this was for the UK, but let's go to the next slide, and I'll have Antti describe the motivation from Bohr behind this product and how things are going.
Yeah. Well, I see this Advantage product as essentially a commissioning tool for anaerobic digestion plants and CHP engines. So while there are plenty of portable options for doing spot tests, the reason for engineering something like this is that you can leave this running on the site for, say, 3 days or a week, just like it was an in situ continuous monitoring probe, but you don't need to have those 1.5 inch sampling pots for inserting a probe. You can just take the gas from a 1/4 inch fitting that's typically readily available, and the data is stored inside the Advantage system in its internal data logger. It can also put that data, for instance, into Bohr's cloud-based service. So for somebody who would set up and commission a new CHP engine installation, or like a new upgrading system, this would be something that they could take from site to site and leave running 24/7 for as long as the commissioning lasts.
Yeah, excellent. I mean, it's super versatile, and it really doesn't matter what the application is here too. It's you know, it can be the digesters, upgrading plants, and even carbon capture applications. All right, so we'll get through to, let's see, the next one here, if you don't mind. Speaking of carbon capture, this is one of our first carbon capture applications, which is at the Copenhagen Center in Copenhagen, Denmark. The Amagerbach waste incinerator plant is a waste to energy plant outside the town, and with partnership with the Danish, the Technical University of Denmark.
Yes.
What they were doing here is, this is somewhat of a pilot plant where they tested, I think it was over a dozen or 13 different carbon capture system configurations to find out what was going to work best for waste incineration. Now, with natural gas plants and, you know, biogas or RNG upgrading systems, those types of, and other point source carbon capture applications, those processes are more well known. The waste incineration is a little less experimented with, and so these people were really striving to find out what the financial viability was of that type of application. Next slide, please. Yep, it's been operating for quite some time, and here's a picture of one of their test units. And then I'll just let Antti take it from here with a little bit more detail about what they needed from us.
Yep. So this system here was engineered by the University DTU in conjunction with Danish Carbon Dioxide Union, which is actually a branch of Pentair. So this was also a collaboration with Pentair, and what they are doing is a water wash scrubber for dissolving CO2 from the flue gas and then releasing it in a flash column from water, which is then recirculated into the stripper column. And the whole system is fairly modular. So it basically consists of a couple of shipping containers and then the scrubber towers, which you can erect on site. And they have used this not only at the Amager waste incinerator, but also at biogas sites. So the same configuration can also be used for upgrading RNG. So in many ways, carbon capture and biogas upgrading into RNG are very similar processes. They are both designed to take CO2 away from other gas streams.
All right, very good. Yeah, this is a project we're pretty proud to be involved with. The Copenhagen whole site is actually pretty unique too. The picture in the original slide, and I mean, you can find this online too, but because it's so close to the city center, they wanted to make it look attractive, and it did, because they had very decorative kind of sides on there. It's also a ski hill in the wintertime, and then in the summertime, it's a rock climbing wall on one side. So that kind of speaks to me too. Moving on, I'll go to the next slide, and we'll talk about a little bit of one of the utilization cases for carbon capture. Now, one of the larger CO2 emitting industries in the world is concrete manufacturing. And I believe it accounts for about 8% of all the global emissions. And I think it's almost a 1-to-1 with tons of concrete produced or tons of CO2 produced.
Yes.
Don't quote me on that, but it's equal. And so it's a lot of scrutiny going into this.
Yeah, that's especially in manufacturing of Portland cement, from which concrete is made. So in the clinkering process, you release carbon dioxide from limestone itself, and then as you need very high process heat, you can't do that with electricity, so you need to burn something. And when you burn that something, it might be coal or pet coke or waste materials, you have large CO2 emissions. And you can't avoid that, because part of the CO2 released from the mineral that's inevitable, and also since the temperatures involved are so high, you need a combustion process. So that's a hard to abate industry, one that really benefits from having post-combustion carbon capture, removing the CO2 so that you are not letting it escape into the atmosphere.
Yeah, and then we have to do something with it. So next slide, please. So bringing this into a little bit more of a circular economy of cement and concrete production. In precast cement production, like these cinder blocks and things like that, the CO2 can be supplied to the curing concrete, which will absorb the CO2. So there'll be special curing chambers, and Carbonate has developed a specific version of that. So if you would bring it to the measurements and what's needed in that type of operation.
Yep. In this case, the precast concrete elements are cured in chambers that are roughly the size of a shipping container, and they need inline CO2 analyzers in the ducts leading in and out of those chambers, so that they can track how much CO2 has been bound into the concrete. So the requirement is for a simple low maintenance CO2 transmitter that can be installed directly on the duct, and it needs to react fairly quickly, because when they change the flow rates, we see a kind of a pulse in the CO2 trend. So having a direct reading instrument instead of a sampling system is an advantage. And at the concrete mixing and pouring stations, they don't really have instrument technicians there. So it needs to be something that basically runs by itself without the need for continuous maintenance or looking after.
Yep, so versatile in situ low maintenance probes, that's pretty much what we offer, and it certainly fills a niche in the market. Having something real-time, full-scale. I know this application is a little outside the normal American Biogas Council audience's experience, but we just wanted to highlight one of the things where we've actually found success, and there's a market developing for the captured CO2 that you guys produce or might capture in the future as you kind of adapt these systems to try to lower the overall carbon intensity of your projects. So next slide, please. Just wrapping up the discussion, I just wanted to highlight some of the benefits to end users here. For these MGP 260 series probes, it is a low cost, low maintenance, low total cost of ownership, simple to install, reliable, continuous measurement of some of the more critical parameters for these applications. They are uniquely corrosion resistant. The world's first humidity measurement in the presence of H2S is a risk management type of measurement. So you can protect your CHP from high levels of humidity and your membranes from potential condensation before compression and injection into the membranes. We have, again, no sampling lines, sampling systems. You don't need to sample condition, and no calibration bottles connected to these systems. We do recommend the annual check, just for sanity. That can be done in the field. We have an easy PC software interface that we're quite happy with, that makes configuration of these things very easy. So thank you for that. We'll move to just the next sample thank you slide here, and we'll get into some of the questions that we've received during the presentation, which we have a few.
Oh yes, there are a few new questions.
Which is great. So let me pull this so we can read them easily. And part two to the one question about the pipe diameter is a popular question that we've gotten a few times here, which is the adherence to the biogas regulatory reform rule, the EPA's so-called GC rule for the renewable fuels standard measurement, and the alternative measurement protocol submissions. So we have submitted our AMP. It is in process with the backlog of a number of our competitors. There is an AMP website that you can check, and you can see our submission on there. We are anxiously waiting for approval on that, but actually, you know what, I'll let you describe what we went through as far as testing and what some of the results were on that.
Yep. So in order to sufficiently document our claim that the MGP gives comparable or better accuracy than a GC, we ran comparison tests as we have our own extensive R&D laboratory where we happen to have also gas chromatography instruments. We did parallel testing between 2 MGPs and 2 runs of the GC. We were using a methodology that was developed originally for validating alternative measurement technologies for emissions monitoring. So the approach is a little bit similar to a RATA test in North America, relative accuracy test assessment, but it's more extensive. And the benefit of that test approach, it's documented as a European standard EN 14793, is that it assesses both the accuracy and precision of both our method and the GC. And I'm happy to say that we got better scores for both precision and repeat and overall accuracy compared to GC with manual sampling. So in the GC method, we took 5 parallel samples for every half an hour average of the MGP reading and analyzed those. Those results were presented also at the Renewable Gas Technology conference this summer. I had a poster there. So it was an interesting find, because while we were concentrating on the raw biogas concentrations, 40 to 60% methane, we did this also for the high end for basically RNG concentrations, and the results were equally good, up in 90 to 100% range.
Yeah, so yeah, we jumped through all the hoops. We have a long submission. We're as good, if not better, in many regards to the GC, and so our application is sure to sail through as soon as they get to it. But all right, so I think that well answers that question. Stay tuned, of course. We're going to keep anybody who is on the edge of their seat updated, so I can happily add you to my list of people who are waiting for an update. The next question comes about the methane slip and actually explaining what that is, and then asking about the Pentair case. So just really quickly, the methane slip is the methane left over in the tail gas. And so any upgrading system is going to have some leftover methane, whether it be amine stripping, which is still very slight. There's always going to be some. Membranes are typically 2% or less of methane in the tail gas, and then PSAs can have some more, but there's a lot of great PSA systems out there that are getting to really low methane slip measurements. So essentially, it's just kind of wasted gas or emissions that we want to avoid, and you can optimize your system by measuring the slip and recirculating. So
yes, especially for membrane plants, the proportional valve that loops some of the gas back to the front of the membrane cascade, you can adjust that based on the slip. Of course, you want the slip to be small, but if you are pursuing it down to less than 1% slip, you might be actually wasting lots of electricity in that you loop the gas excessively. So there is like an optimum level that you want to maintain. And this measurement is also important, not just for optimizing the upgrading plant, but if that CO2 is then sold off as a commodity, as a feedstock for something else, then you need to also know its quality. Some of the technologies that have higher slip, like PSA compared to amine scrubbing, they would then probably use an RTO to burn off that methane into carbon dioxide. But if you do run an RTO, you want to have a real-time methane measurement between your upgrader and the RTO to give you advance warning if you have excessive amounts of methane going into the thermal oxidizer.
Yeah, very good point, and an application that we've seen a little bit more interest in, because one of the key things there is the response time of that measurement, so that you can make control decisions. Our probes have a very fast response time, slightly flow dependent, but we can evaluate your system individually and kind of provide better expected response time numbers. But long story short, it's going to be better than a minute, and we've had some success with people preventing their RTOs from overheating. Let's see, next, we had a couple of questions here about just function and installation. Are there multiple channels available for pressure, temperature, etc.? We do have an analog input. It can be pressure or temperature sensor, and we can relay that signal out of the probe too, depending on the analog channels you prefer to use, or through the Modbus RTU communication. So we do have options there. The next question about installation was about straight run requirements. It's usually about 3.5 pipe diameters from a bend on the downstream, and then 2 on the upstream.
Actually, it's the other way around. It's the recommendation in our documentation is for 5 diameters of straight run upstream and 2 diameters downstream, but people have used shorter runs. So for instance, in that Miura case from Japan, they had approximately 2 upstream and 2 downstream, and we didn't see any adverse effects. We basically took the guidance for straight run requirements from flow measurement standards, figuring that if the location is good enough for measuring flow, then it's definitely good enough for measuring gases. And gas concentrations in turbulent gas, they even out very nicely. So those are just recommendations. They are not absolute hard limits.
Yep, and kind of flow dependent too. Just want to avoid some turbulence, but for the most part, low flows in these kinds of systems are not a problem. Last functional question was heart compatibility. No, we're not heart compatible, but just 4 to 20 loops and the Modbus RTU.
Yep.
All right, and then the last question we'll wrap up was, let's see. Nope, I'm sorry. I needed to scroll down. Let's see what questions we have here. Let's see. For AD applications, does the size of the digester matter? No, it does not. So we're very versatile. We don't require any flow rates or anything like that. So any types of systems will be fine. And let's see. I think we addressed the tail gas measurement. Do you have any comments on the mass balance?
Yep. Usually we measure or we offer probes for measuring the raw biogas that goes into the upgrader, and then the tail gas measurement, and the customers would have BTU meters for custody transfer purposes. And my understanding is that they generally tally quite nicely, typically within the accuracy of the instrument. So we don't see any large discrepancy in the concentrations. But of course, when we are doing a mass balance, one has to take into account also the flow rates. So for doing this, we tell you the ppm or volume percent concentration of the gas. In order to do a mass balance, you also need to know the flow rates. But if you take into account 1 or 2% accuracy in the gas measurements and the accuracy of the flow measurement, we are within that combined uncertainty typically.
All right, very good. And let's see, we had a couple questions on price. We're going to avoid those just because this is kind of a public thing, and this does live on the ABC website and perhaps on YouTube too, so we don't want to fix any pricing here. Then let's see, I think the last question here is about the CO2 ecosystem. Let's see. Let's see, technologies for upgrading biogas systems to include carbon capture. So, you know, we want to see it happen. We're not able to give any real specific guidance on that. We would encourage you to work with the engineering firm that perhaps you already have been, or somebody who kind of specializes in those types of services. And then we'll be happy to offer some measurement solutions for whatever system is appropriate for your type of biogas upgrader.
Well, we have seen some of our customers using the separated CO2 stream to produce more methane, either with biomethanation, where you feed that CO2 together with hydrogen into an anaerobic digester with a modified set of bacteria to produce even more methane, or that CO2 stream can be used in an inorganic Sabatier reaction for producing e-methane. Especially in Japan, that technology is advancing very rapidly, and it's planned to free them from relying on RNG imports by 2050.
All right, so I hope that answers your question somewhat, and that brings us to the end. We'll just put the next slide up, if you would. And we're a couple minutes over the 45 that we had targeted, so we thank you for all your time and attention. Please reach out to us at vaisala.com or myself. I'm on LinkedIn, or I think my contact information might be part of the handouts here. But otherwise, once again, thank you again. Thank you, Antti, for hosting us here in the headquarters, and we hope to see you all at some future events. So thanks and take care.
Thank you all. Thank you, Vaisala.
Thank you.
Yeah.